Okay, the final presentation before lunch is from Michael Flynn with the NASA Ames Research Centre. And Michael's going to speak about water recycling technology that's been developed at NASA. Michael has a distinguished career within NASA, has been responsible for a number of the water recycling projects which have been deployed by NASA in the space station. And in fact has worked with many of the companies here today, which is quite interesting to see those kind of real-life applications of what's being developed for applications in space. So Michael, welcome and thank you very much.
Thank you. Okay, so you're probably all wondering, what is a NASA guy doing here at a water conference? My objective is to explain that to you, so hopefully by the end of this presentation you'll know what I'm doing here, and you'll have a little understanding of some of the projects that we're working on and are funded by NASA and the federal government in this area. I work at NASA Ames Research Center. We're a research center. We don't launch spacecraft. We don't manage astronauts or manage missions. What we are is the front end of the technology development pipeline. So we're primarily working on missions that are going to be way out in the future. So most of the water recycling work falls under the category of what's called advanced life support, and that is basically everything that's required to keep an astronaut alive in space, and that's water recycling, air recycling, solid waste, power production, space suits, basically everything on the inside of the spacecraft we have responsibility for. And our objectives are a little different than most private companies. Our objectives are primarily keep the astronaut alive. It's very embarrassing when you kill the astronaut, so we don't want to do that. We also need to provide a habitable environment. Astronaut time bills out right now at about $10,000 an hour. So we need to provide a very high quality environment for the astronauts to function in so we can get the maximum amount of work out of them because it's very expensive. And then finally, reduce cost. We could send people to live on Mars right now. We could have permanent human colonies on Mars. We have the technology to do that right now. The problem is it's way too expensive to do that. So a big focus of our work is to reduce the cost of human spaceflight applications. So traditionally, NASA water recycling, air recycling was what we do here on Earth. You get a tank of clean water, you make it as dirty as you possibly can, and then you dump it somewhere. Most NASA programs did that. Of course, we used a feed tank and a product tank to do that. But that all changed recently with the International Space Station. On the International Space Station, that's a permanently manned facility orbiting right now above us with 6 crew members on it, has a 10-year life, and it costs about between $10,000 to $70,000 a liter to bring water up to that International Space Station. So we're going to do water recycling, and we're going to do it big time. We're going to close that water loop. If any of you want to be astronauts, doesn't look like anybody does, you have to be willing to drink your own urine. And not only that, you have to be able to drink the person sitting next to you's own urine. And to make it even more disgusting, the oxygen you breathe, well, that's also coming from your urine too as well. So we do a lot of water recycling on the International Space Station. Now for a Mars mission, that's a 3-year mission with no possibility of resupply. Resupply costs there are about $140,000 a liter. So there we're going to completely close that loop. We're going to have 100% water recycling. You're going to bring a cup of water, and that's it. You're going to take a breath of air, and that's it. And you're just going to recycle those over and over and over again for a mission like that. So what is life support? Well, we have our inputs. What do you need to stay alive? You need water, you need oxygen, you need some way of getting rid of waste, temperature control, you need a pressurized environment, and you need energy. And as you might guess, we're going to get those from your outputs. We're going to get the water from wastewater. We're going to get oxygen from carbon dioxide and water from carbon dioxide. We're going to destroy volatile organics. Solid wastes are going to be recycled, and heat is going to be recycled into energy as well. So how do we do this? This is a flow diagram of the International Space Station system. I'm not going to go through it in great detail, but I'm just going to go through a little bit of it. Here's the key. Here are the human beings, and they are producing urine. They're producing solid waste. They're breathing. So they're producing cabin air. That cabin air has CO2 in it, and it has humidity condensate in it. We're going to strip the humidity condensate out of that and recycle that back and recycle that in our wastewater treatment system. We're going to take the urine and recycle all the water out of the urine. The solid waste we just store right now, but we have plans to actually recycle the water from the solid waste as well. The CO2 is removed through a CO2 removal system. Then we reduce the CO2, and we get hydrogen from our oxygen production system, mix that with the CO2 to produce water that then is recycled. Also, we take a little bit, the oxygen is generated from some product water. We electrolyze we electrolyze the water, produce oxygen, and the hydrogen we're using the CO2 system. So it's a very closed system. Currently, we're getting about 85% closure on this system. That means 85% of the mass that's required to keep a person alive, or recycling in space. That system's been in operation since 2009. It runs 24 hours a day, 7 days a week, 365 days a year. Now, of those resupply requirements, of those issues, water is the big one. See, 85% of the mass that a person requires to stay alive is water. You folks do talk about money, right? How much money can you make? What's the market? Well, we do it something different. We talk about mass because we want to launch this stuff, right? Mass and money are kind of the same thing, though, really, because they basically, it's the cost of the vehicle to get there. But we're not, federal government, allowed to talk about money because that upsets the taxpayers. We don't want to have a revolution. So most of it is water. So water is where NASA's invested an awful lot of money since about 1964. Something like about $10 to $15 million a year has gone into developing water recycling technologies. So that's a huge amount of money. We've looked at most water recycling technologies, and most of that stuff sits on the shelf right now collecting dust. So here's the ISS water recycling system right here. It's a physical-chemical system. We're using primary distillation to treat urine, and we're using absorption-based technologies to treat the humidity condensate. The products of those two systems are then combined, and we use a thermal catalytic system to then make sure that we get all the volatile organics out of it, and also that's very integrated to our control system. One of the things about the International Space Station system is it has to run unattended. There has to be no human interaction with it. It has to run automatically. And we can't have any failures, or we can't have any false negative, we can't have any sensors that are saying the water's not safe to drink, because what are you going to do? You're going to abandon the space station? No, you're not going to abandon the space station. So we can't have a lot of sensors. So the whole system has been integrated and designed to prevent those things from happening. So for instance, we use a catalytic reactor, and one of the reasons we use a catalytic reactor as a post-treatment is so we can use a simple conductivity sensor to determine whether we're producing potable water or not. So this system is designed that if it's running, meaning water is coming out, that's potable water. If no water is coming out, well, that's not potable water. There's something to be said there for transferring that to commercial applications, because often for small-scale water treatment systems, labor turns out to be your cost driver in those applications, not the actual cost of the technology. So here's a great picture. This is the first day when they got to drink the recycled urine. Look how happy they are. Look at those smiles all around. They got the little bags of recycled urine there. They're all drinking each other's urine, very happy. Actually, that's not correct. There you go. That's the right picture. I make jest about that, but I want to drive home the complexity of this. For instance, pumps don't work in microgravity. None of the pumps that you commercially use here work in microgravity. None of them do. Imagine if I took the toilet out of the bathroom and I bolted it to the ceiling and said, now go to the bathroom. It's a very complex system, very extremely complex, very mechanically complex. And that is the problem. This is a picture of the International Space Station, inside the International Space Station. It's extremely complex, extremely mechanically complex. Our biggest problem right now is that maintenance requirements are about 24 hours a day. And so that doesn't leave a lot of time to do science. And so a lot of our advanced technology, our advanced research is get the maintenance out, get the human element out, develop extremely reliable systems as much as you possibly can. We've had a couple of pretty significant failures of this system, most of them early on, like within the first couple of months when we brought the system on orbit. I'll talk about one of them right here. This is the distillation system. This is how we treat urine. And you can see right here, this is calcium sulfate right here. And this urine distillation system plugged up with calcium sulfate. We had to return that to Earth, get somebody to chip out all the calcium sulfate, and then put it back up on the International Space Station. Very, very embarrassing. And very, very expensive, about a $100 million failure right there. Here's a picture of calcium sulfate, two types. The green type, we call that Russian calcium sulfate. And the brown type, that would be European and American calcium sulfate. The calcium sulfate comes from the fact that when you take a person and you put them in microgravity, they lose bone mass. They lose calcium in their bones. And that comes out in their urine. And also we give them calcium supplements to try to prevent that from happening. So we get a whole lot of calcium coming into our distillation assembly, and that causes a lot of problems. So that's bone right there, reformulating bone. Astronauts don't like that when I show that presentation. They frown at me and get upset. So we have a project right now to mitigate this problem. We can't have this calcium sulfate plugging up our water treatment system. It's a very, very bad situation. And what we're doing is a technique called electrodialysis metathesis. It's an electrodialysis system, allows us to selectively remove calcium out of solution. Basically, we're using an electrodialysis system. On one side, we have membranes where we put the wastewater, and on the other side, we put sodium chloride, and we just exchange calcium for sodium, and we exchange chloride for sulfate and carbonate. Pretty simple. It's actually commercially available technology, used a lot in zero discharge desalination applications. What we're doing that's different is, of course, we take urine and we recover 85, 90% of the water out of it, so it's like a syrup. It's syrupy, disgusting, all the worst parts of your life, urine. And we're developing membranes and systems to resist fouling and failures, premature failures due to those applications. There's another technology, actually a replacement for the International Space Station, called VIPCAR, vapor phase catalytic ammonia removal. This is the big hammer approach to wastewater treatment. This system will take basically anything and produce potable water out of it. It works on basically taking nature and putting it in a little box. We have a distillation system, which is similar to, you flush the toilet, it ends up in the river, goes in the ocean, evaporates the ocean. So we have a distillation system. Those vapors then go up into the upper atmosphere where UV light hits them and oxidizes the volatile organics. And we actually use a catalytic reactor to do that in the vapor phase. And then the water condenses back down as rain, and then you drink that water. We do the added step that we actually recycle latent heat of vaporization because we want to have really low power consumption. This brings up an interesting point about zero discharge or water recycling, which is, you flush the toilet here, and it comes back as rain, right? Next time you walk outside and it's raining, think about that a little bit. You're already recycling urine. You're already recycling water. I know there's a lot of, in the press, there's a lot of resistance to doing that, but the fact of the matter is you already do it. This is another technique. You've heard a lot about forward osmosis. We've been working on forward osmosis, since about 1993. We've been working way too long on forward osmosis. Probably should start moving on. This is a system actually called direct osmotic concentration. It's takes urine, humidity, condensate, gray water, and produces potable water with it. For those of you who aren't familiar with forward osmosis, well, actually, there is nobody who is not familiar with forward osmosis. Forward osmosis is very important to you. It's your small intestine. Your small intestine is a forward osmosis membrane in your body. Your blood has a higher osmotic potential than what you drink, and so water naturally diffuses across the membrane into your blood, diluting your blood and concentrating what you drink in it. For instance, if you're lost out at sea and you drink seawater, well, that has a higher osmotic potential than your blood. Process works in reverse. That's why you shouldn't be drinking seawater. It's a bad idea. But basically what you can think of it as is if we have a little classic little YouTube experiment, we have a membrane between them. And let's say this is salt water on this side and this is urine on this side. The salt water has a higher osmotic potential or higher entropy. And so the system wants to come to an equilibrium. It's just an energy minimization process. So the only thing that can happen is water go across the membrane because the membrane won't allow salt this way and it won't allow contaminants that way. So the only thing that can happen is water goes across the membrane and it'll just dilute out this as much as it can, producing an osmotic potential or osmotic pressure as measured by the rise in the height of the water there. We have another project that's just getting started right now called Next Generation Life Support System. It's a forward osmosis-based system. Basically what we're doing is we're taking a biological reactor, an integrated aerobic, anaerobic biological reactor, and then we're taking the forward osmosis and using that as a post-treatment system. I don't have a picture of that because that's actually a new project that we're just doing right now. Another example of forward osmosis system are these little personal water treatment systems. Maybe some of you have seen these. This is a product made by Hydration Technologies. Basically this little bag here. You put dirty water on one side in the red port, and you put sugar on the green side, and just like in your intestine, the water flows from one side to the other. The sugar has a higher osmotic potential. You dilute it out, and then you drink that right down. We have a modified version of that because we're more disgusting than most people. We actually have a version of this where you put urine in one side, and you guessed it, we're going to make lemonade out of it. Got to have a sense of humor in this business. This is an example of flight experiment. We're looking at forward osmosis in microgravity applications. This was actually the last experiment ever done on the last space shuttle mission, and we're just looking at flux rates and the issues of concentration polarization in microgravity. We also have a forward osmosis system right now at Ames Research Center that we've installed in a green building there. This is a LEEDs Platinum green building that's being installed there. Actually, the building just opened, and we're installing the water treatment system right now. It's a forward osmosis system. We're taking all the hygiene water and purifying it to potable standards, but darn that state of California, they won't let us make people drink it. It's not like astronauts. So we're just using it to flush the toilets. That reduces the water consumption of the building by around 50%. Osmotic distillation, which is also a forward osmosis-based process. In this situation, what we do is we take a membrane. On one side, we put the feed water. On the other side, we put concentrated salt water. And we use a particular type of membrane that has a pore size that allows a meniscus to form on both sides of the pore. And so we actually distill the water through the pores of the membrane. That technology is what's called isothermal distillation. There's no temperature difference across it. We're just using a salt gradient across as it. And it has the unique advantage that it produces much purer water than normal distillation systems do. Exactly why is still up to debate. I have some students, some of them that are here, that are doing actually their thesis, trying to understand exactly why we get such high organic rejection, such high reductions in TOC using this compared to like a normal distillation system. We do a lot of work on membranes, advanced membranes. We don't actually make our own membranes. What we do is we work with the community and we test membranes that people give us. Some of the membrane companies that you've seen here we're working with. We're working with lipid-based membranes, the aquaporin membranes. We just actually completed some testing last week on aquaporin-based membranes. We have some work on glass membranes, nanotube membranes, osmotic solids, which is like making a sponge that you could just put in salt water and then you squeeze the sponge and you get fresh water coming out of it. And then also novel backings to address an issue called concentration polarization, which is a big problem for osmotic elements. Ultimately, my vision is, normally if you have like an RO membrane, it's good for 3 to 5 years, and then you have to replace the membrane. But let's talk about that small intestine of yours. I don't know about you guys, but I plan on living for about 80 years. And I don't intend to replace that membrane in 3 to 5 years. I intend to leave that the way it is. And you're going to go eat steak here at lunch or whatever we're going to have. Well, actually, this is San Francisco, so tofu. You're going to be eating tofu here at lunch. And that's pure solid going right into that membrane, right? And it's not going to foul that membrane. It's probably going to damage the membrane. And then you're going to drink a cup of coffee afterwards, and you're going to separate out the water from the inorganics in that membrane. Well, the way that works is that membrane is alive, and that membrane is a lipid-based membrane, and it's got bacterial mammalian cells attached to it on the backside of it that express those lipids, and so they're constantly replacing, constantly regenerating that membranes. And so we're interested in developing a quasi-living membrane, a membrane that's really not alive, it's not dead, it's kind of in between. We're using a synthetic biology program to fund that activity. And the idea is to generate a membrane that can last, be very reliable, you can't damage it, fixes itself, and lasts for many, many years. We also do a lot of commercialization. Typically, NASA, we don't actually do commercialization. It's not our bailiwick. We do our NASA thing. But oftentimes, companies that we work with do commercialization, or people come to us and want access to our technology and do commercialization. This is a distillation system. It's called white film rotating disk evaporator. Sorry for the darkness of that picture. It's probably one of the most efficient distillation systems thermodynamically in existence right now. Also uniquely designed to handle high solids waste. So this system has been used in the oil field applications and produced water treatment. It's also been used in food processing applications, primarily wineries that want to do closed-loop water recycling. This one here is taken from a picture of a winery where they had a closed barrel washing system. So they'd wash barrels, they'd recycle the water, purify the water, make potable water, and then wash more barrels and just have a completely closed system. We found that to be a market where there is possibility because these are industrial facilities and they just do it. They don't get permits. They don't talk to the state. They just do it on their own. Oh, sorry, that picture didn't come out. But what you would have seen here is a seawater desalination system. We've done some work on seawater desalination. Our area of expertise has been primarily developing seawater desalination systems that do not have negative environmental impacts. So we have a forward osmosis-based seawater desalination system that does not produce a concentrated brine byproduct. It does not entrain and kill the organisms of the water that go into it, and there's no solid waste that's going to any solid waste treatment plant. We also have some work in biological fuel cells. This is primarily, we have a collaborative agreement with Craig Venture Institute where we're doing genetic engineering for biological fuel cells, and also Stanford University as well. Craig Criddle, who you'll see a tour tomorrow, we're also working with him. We have a grant with him that we're putting in place. We take it a little bit different. Our fuel cells, we don't want to consume oxygen because oxygen costs us money, and we certainly don't want to produce carbon dioxide because carbon dioxide costs us money. So we're heavily investing in genetic engineering to actually produce like bioplastics, to take that carbon dioxide, take that carbon and put it into a solid media that's removed, or potentially a fuel byproduct on it. So we're doing heavy genetic engineering on the cathode sides. We also work with Statecraft on osmotic power systems. We had a grant with Google looking at developing osmotic power systems primarily for wastewater from wastewater treatment plants to extract energy out of when you dump your sewage into the salt water, into the ocean. There's a potential energy there. We can extract that energy out of it. And then we do work on ammonia fuel cells, and this is actually, you could buy a fuel cell-based car, but the problem with your fuel cell-based car is you got to go to the gas station all the time. And the idea is to take hydrogen and turn it into a liquid by converting it into ammonia, store it under low pressures as a liquid, so you get about the same energy density as gasoline. So now your car will go 400, 500 miles. We can actually take it even further. We can turn it into urea, which is a solid, those little pellets you put on your lawn. That's urea. And we have developed a way of actually rapidly converting that urea into ammonia, and then the ammonia goes into alkaline fuel cell and you produce electricity out of that. That also has applicability for wastewater treatment. When you have urea in the wastewater treatment, just use the alkali fuel cell, and one of our projects actually has that integrated into it right now. And I'll end here on this one. One of the areas that we do technology transfer we're very interested in is third world applications for disadvantaged communities. That does fall within our government realm. And so we have a project right now where we're looking at using forward osmosis to treat sewage lagoons in developing worlds, in Navajo reservations, Eskimo communities throughout the world, Palestinian applications, Arab applications. And there what we're doing is doing it for agricultural purposes, where we take fertilizer, concentrated fertilizer, and we use that as the draw solution, draw all the water out of the sewage, dilute down the fertilizer, and then use the fertilizer to grow plants. What we've learned from a lot of our work in third world applications is that it's important to have a sustainable economic model, meaning you can't just deliver a water treatment system that doesn't produce any revenue, because as soon as it breaks, nobody's going to fix it. So you have to provide a whole package. You have to provide a package that provides the ability to provide some level of revenue in the system. And so this project is designed along those lines to enable agricultural applications. So that's where I'll finish it. I know lunch is coming up. I don't want to hold you guys too late. So thank you very much.